right, we're at the last talk of the day, which is going to be from our Allotrope product team connected domains model update. And this is part of the Q2 candidate release. So over to you, Wes.
Thanks. Yeah. So last dance, right? I'm here to talk about some of the work the Allotrope product team has done on the connected domains model. Probably the first question we should answer or address is, what is the connected domains model and why are we interested in it? Allotrope's done a really good job of structuring, standardizing, and semantically defining analytical instrument data. And there are a few good use cases that are constrained to that area, but it's just a few. Like, is a particular method still performing well? Is an instrument about to go out of specification? You can answer questions like that. But most of the use cases require that you know the context of the sample to be able to answer the relevant question. So if you have two samples from a process chemist, one of them is 90% pure and the other is 99% pure, that's not really useful. You have to know that one of them was recrystallized from ethanol and the other was recrystallized from IPA. And that metadata, that sample metadata, is stored in many different systems, usually. Different systems across companies, but even different systems within a company. And because you have different systems, you have inconsistent terminology, and you have divergent data structure. And that usually means that assembling the data is complicated, error-prone. And if that assembly is complicated and error-prone, then critical context and lineage is often incomplete or missing. And that means our scientific data remains fragmented. This fragmentation limits decision-making, AI readiness, etc. So the idea was, if you start out with your analytical results-based ASM, you can expand the scope of that and address some of these connected domains. And the connected domains model was meant to be like a high-level scaffolding above, so that you could structure this data and make the necessary links. Most of this came from is an expansion of the work that was done last year on the ELN model. Just pointing that out, that this work has been going on for quite some time. And the goal is to federate all of the content to get rid of the problems that we just talked about in the last slide. What are the potential uses of a connected domains model? Well, the AFO terms themselves are going to be useful, right? Vocabulary for software configuration. The AS schema themselves could be data models for software design. The ASM files could be the framework for creating semantically consistent data products, and they can be a blueprint for semantically consistent knowledge. And the idea here, as we've heard, is important many times in the last 2 days, is that the context and the connectivity is done early by design, and you're not trying to piece it all together at the end, where it's much more costly and more likely to be error-prone. So if we just take a minute to look at the objects that are in this domain, if you start at the top, you have the concept of a program. A program is made up of projects. Projects is made up of studies. Studies are made of experiments, and then experiments usually have one or more assays associated with them. And then alongside that, you have materials and equipment that are important to each one of those concepts. And basically everything has a specification attached to it, right? And then very loosely, we've just put some borders around this to show the work that's already been done and the work that's going on now. So we have the ELM work that morphed into this work on defining studies, the CMC workflow, and then the digital analytical methods has all happened already. So if we take a look at what's happened in terms of in an ASM, right, those concepts all turn into documents. You have a program document, a project aggregate document, project document, etc., all the way down into your actual, you hit your analytical analysis ASMs. So what was the goal of this work? the task that the product team was given was, can we provide robust semantic definitions of these concepts and the subcontexts that come out? And can they be, can we do this so that they're consistent with the ontologies that we've been working with all along? Also, the directive was that let's pressure test this with a few studies and make sure that we don't have significant gaps in that scaffolding. And finally, what are the real key connection points between the ASM and these connected domains, and in some cases between the connected domains themselves? So moving on. So let's start at the top. What is a program and what is a project? Program was not an AFO term, so we hadn't addressed that yet. Project was a term. It was it's a project, it's a planned process that is undertaken or attempted to meet some requirement. But we just had the human readable definition. We didn't have any OWL restrictions on it. So as far as AI would be concerned, or a reasoner, it was just a planned process. So we reached out to my new best friend, Claude, and asked Claude, is there a consensus out there in general, but also specifically in ontologies, what these two concepts mean? And I was actually pretty impressed with what came back. Number one, perhaps because I said make sure you're consistent with the oval foundry, but nailed where it connects into the BFO. It's exactly where you would think it would go. Picked up that a program is something bigger than a project. Picked up that a program is something strategic, and a project is something more tactical or has a deliverable. And then gave some, the completion criteria and the governing aspect comes from that whether it's strategic or output based, and then gave some examples, and all of that seemed to fit real nicely. So then said, okay, go ahead and create an AFO term. Go read the AFO guidelines on term definitions and spit out some terms. It's a little wordy, but I think it did a really good job. It definitely caught that the program has an objective specification, a strategic specification, and that projects were probably part of the program. And then the thing that was really wanting to change the definition to say that a project it's delivering some output. And then if you get specifically, then going specifically into drug development programs, what some of the metadata associated with those two things, program to therapeutic areas usually tracked, mode of action. And for a project, the modality of the compound you're looking at, what the indication is, and where it is on the clinical trial status. Right? And it actually told it to pay attention to Allotrope members, and it went out and pulled all of the pipelines, the published pipelines for all the Allotrope companies, and came up with this list of metadata that we should try. Then moved on to study and experiment. Here, Allotrope had a definition for an experiment and basically just imported the SIO definition, which is an experiment. It's a planned process for verifying, falsifying, or establishing the validity of a hypothesis. Okay. Didn't have anything for study, but I thought let's go back up to SIO and see what SIO had to say with that. And the definition of study is a process that realizes a study design. Not quite great. And then when you look up the definition for study design, it just starts out that a study design is a protocol for a study. That's all kind of rather spiritual. So I reached out to Claude again and said, do we have a consensus? Can we make these a little better? Claude had a lot more difficulty with that. And we had a lot of back and forth and some offline discussions with SMEs on how to do this, but I think we finally got somewhere. And the main thing that came out of it is study usually has some predefined protocol that says what you're going to do. that seemed to be consensus. And the other consensus about a study is that you have one or more parameters, one or more things that you're looking at, and you're varying to see what the impact that has. And then just for experiment, it also included the definition of assay and test from the AFL. Frankly, I think we need to spend some time on that and tighten up those definitions a bit. And we need to differentiate, like understand that if we go with this definition of experiment, which is to verify a hypothesis, that not every entry in a notebook is going to be an experiment. So we may have to have some super class above all that, just say that you're recording information. So if we reach out and look at examples of studies for drug substance and drug product, and the corresponding regulatory guidances there, they all seem to meet that definition of study, with perhaps the exception of a structural characterization study and the reference study or reference standard characterization. But even then, you could kind of say, well, the parameter is the analytical technique, and what has to come out of that is that it doesn't conflict with the structure, whatever the result is, right? It doesn't. But the other way to look at that is maybe in the allotrope world, those aren't actually studies or something. Okay, so now if we go back to our ASM, and we take that plot that we had there, and we put some foreshadowing, stretching, and spaces in there, we can show what happened when we really started looking at these studies. And we did find a few gaps. One, if you have a study protocol, it's expected that you track any deviation from that protocol. So we needed to add a document and some terms around recording these exceptions and these deviations. There's also that the concept of a study point becomes very important. That could just be the experiment, but then we have to augment the information that is captured with the experiment. And then the other thing that kind of jumped out was that study protocols, especially coming from regulatory agencies, they don't talk about the area percent of the peak that has the role of main component. They say it's purity or assay, right? And so we probably need to have some linkage between the terms that are coming off the instrument and what you're actually putting in a report. So just real quickly, for those that are not familiar with what a drug substance stability study is, this is one of the ones, the data sets we looked at, because we were also tasked with pressure testing this, seeing if we could break the model. But a stability study is just something that the regulatory agencies and the companies themselves expect. It's just to make sure that the drug substance or the drug product retains its identity, strength, quality, and purity throughout whatever your shelf life is, right? And typical things that you track here, at least for drug substance, you track, you have a temperature, you do it at a certain temperature, you do it at a certain percent relative humidity. You usually have to do multiple lots. We can do multiple lots because that's a lot of work. And you typically have time points so that you can track, and if things start to go south, you at least know how long it takes before you start to get in trouble. And then you usually predefine exactly what tests you're going to do before you do them. And you probably, it looks like you probably can read it, maybe, but that's just an example, like snippet out of the ASM. And then we did the same thing with a polymorph screen, a little bit different. For those that aren't familiar, most chemical compounds, small molecules at least, can exist in multiple crystalline forms, and each crystalline form has its own solubility, stability, and bioavailability, even though it's the same molecule. And after a couple of pretty bad incidents in the past, both pharma and the pharma companies and the regulatory agencies really want to make sure you understand what crystalline forms are possible and that you're using the most stable form, right? So a typical screen that you would do is it's what's called a slurry screen. You make up a slurry in a bunch of different solvents. You let it hang around for weeks because thermodynamics is not always the quickest thing, right? So you let it here 4 weeks, and then as another study parameter, it's a little bit different because here the sample preparation is actually a variable that you're changing. You look at it wet, and then you dry it to see perhaps if you had a solvate or a hydrate before, and you dry it now to an anhydrous form, so you pick up all that information. The other thing that kind of jumped out when we looked at this was for our analytical method is you have like contingent testing. So, if you find a new polymorph, nothing went wrong, there's no deviation, but there's additional work that you have to do. And so one of the things we have to do is figure out how to capture that. Going to buzz right through this real quickly, but just wanted to show that we did our due diligence. When we put all that information into the ASM, we were able to query it all back out again. So here's all the study information that include electronic signatures and the exceptions. Here's the query where we pulled out each of the study points with and what the parameters were at each of the points. And then here's the results that you could pull out. So now if we start looking at how, the third thing that we said we wanted to look at is how we can link into these connected domains. There were really 4 things that kind of stood out the way you could do it. And the first one is just build a big ASM, put everything in the ASM. The second option was, well, let's just have a study ASM that has the scaffolding, and then you link to all of the analytical ASMs behind that. The third option is a lot of this may be tracked elsewhere in other systems, right? So use the fact that it's in another system, but now use the defined ontology terms and make sure you have the right links so that you can unambiguously find your data. And then the fourth one is this idea of a virtual study. It's we've got all this data in our data lake. Do we already have this information? Do we have to set up a whole new study? Let's query and see where things are. Or maybe it's going to be for filing, so it has to be rigorously done, and we have to have a signed protocol, but we can still go out there and look, and we can say, no sense doing 35 degrees, because we know that it's going to get information like that. So in all 4 cases, you have this single top-level design that's going to facilitate data capture, data transfer, and knowledge management. And then your scientific data from studies are now connected by design, right? The analytical results have context, and the experiments have access to the details of the analytical results. And hopefully then new insights are a lot easier to find. I'll go real quickly. I know we're running a little over. I'll go real quickly over each of those cases. So here on the left side, you have the ASM. And then on the right side is like your external domains. And yes, you say the big agglomerate ASM, everything's in the ASM. Put all the information there, and that's how it's linked. It sounds maybe ridiculous, but if you take the raw data out and you actually contract with the CRO to do your stability study, or contract with the CRO to do your polymorph, that might be a very good way to get all your data back. And then the second one is you have your study ASM that has, in the bottom left, has all the information regarding the study, and then you have pointers to all the ASMs, right? So if the one ASM is too big, the thing to point out here is now you have to worry about that your identifiers are globally unique. You're either using UUIDs as your measurement IDs, or you're combining your ASM name with the measurement ID, right? If you're writing the converter and you always start out with measurement ID 1, then you're going to run into a lot of trouble if trying to link things, right? The third case is basically what we have right now. You have your ASM and your external system, whether it's a LEMS or one of the larger like platforms like Zontal or Benchling, anything like that. It's maintaining all the linkages. It's got to be the one that goes out. The caveat there is then that system is responsible for making the links to the ASMs. It either does it from the beginning by building your instrument sequences and embedding that information in, or after the fact, someone saying, no, this is the data that belongs. And then for the ad hoc study, a lot of the questions here, we found that in looking at it, that the material actually was very important. And you either had to have direct access to exactly what material was being run in that ASM in order to do these queries, or you had to have a highly performant way of finding out what material or what sample IDs are associated with a given material. If you can do that, you can do these things. You can do things like in the idea of the polymorph study, you could see telling your AI agent, go out, find all of the X-ray patterns for this particular material, bring them back, do a cluster analysis, and then show me a representative XRPD of each cluster that you found. And you could then look at those and say, I've never seen that pattern before. Uh-oh. Right. And deal with it. So that's the kind of thing that you would be able to do if we have all of these linkages. Real quickly here, just some technical considerations with each one of them. For the agglomerate study ASM, there's some JSON limitations, so you can't duplicate a JSON key, so you can't have two LC aggregate aggregate documents at the top level. It's not allowed under JSON. There's actually some argument that whether it is or not, but definitely the tooling doesn't support it. So you have to move those down the tree and attach them to the study points, and then everything works fine. We did that testing, and then that's why it's a light orange, just because we already know the path forward for fixing that. And you definitely have to move the raw data out of and there's somebody then has to move that data into the ASM, whether you've done it automatically but probably there's some manual curation. For skeletal ASMs, it's sort of the same thing. You have to do the manual linkages, but here too, we haven't read that you have to have the unique measurement ID, so it's going to be very difficult to have unambiguous linkages. For the option 3, where everything's in another system, it's the same thing. The unique identifiers are important. I think a lot of the converters are already using UUID, so it's not an issue, but some of them are not. And then for the last one, I think the thing that jumped out is that we really need this material linkage is key to answering a lot of questions that the users will have. Last slide. So where we are, I think we're definitely on track for a CR release in Q2. We talked about it, or I talked about it as we were going through. There's some issues with the AFO that we probably want to address before that, yes, and we still need to review some things. We looked in depth at two use cases do that, and then plus we have all the 2025 work around ELN, CMC, and the digital analytical method work streams. The key finding here was unique identifiers for measurement IDs, and that materials are important. And so now we're at a step, and the question becomes like, how much further do we take this? Do we pause here? Do we issue a white paper? Do we look at 3 or 4 more studies and then take it to an actual release state? Are we happy in just the CMC space? Do we want to look at other spaces, right? And then, the very title, like connected domains. Allotrope shouldn't be doing this in a vacuum all by itself. We should definitely be talking to the partner ontologies and making sure that we're all aligned.